Hi there and welcome back to another chemistry lesson. We're doing redox reactions, specifically looking at half reactions in this lesson. So what I'm going to do is just give you like a general equation. So let's say we have a compound or an element A, and A has a oxidation state of X, okay, and we have another element, we call that one B. So it doesn't matter that it might be in a compound, it might have a zero oxidation state. This is just as general as I can do it. Okay, another element has an oxidation state of Y. Then it's a redox reaction, which means our oxidation states changed, leaving me with A. Let's assume A is the one that received electrons. That means he was reduced, so plus a number of electrons. Okay, and let's say he received N electrons and now he's got a new oxidation state, while B is the one that lost electrons. In other words, he was oxidized. Okay, so B used to have an oxidation state, but now he lost electrons, and he might have lost a different number of electrons. It's not necessarily that the number of electrons that A gains is the number of electrons that B donated. Okay, but so we'll use a different number. So N and M represents the movement of the electrons, how many of them were moved. Now a half reaction describes the movement of electrons for each of the processes. So for example, we have that AX used to be AX, but then he gained electrons, a number of electrons, however many, and then it became A with that number of electrons. So electrons here, I should actually write it as 1 negatives. He gained a number of 1 negatives. This one lost a number of 1 negatives. So he gained a number of 1 negatives, and yeah, this is a half reaction. It just describes the movement of the electrons, and you'll notice here that if something was, again, what happened here is he gained electrons. So on the left hand side we can see there's an addition of electrons to him, which means he is being reduced. So reduced in a half reaction will have electrons added to the left. In a reduction, in the oxidation half reaction, we will have B, and then what would happen is instead of B, he would lose a number of electrons, Me, and that would produce B with his previous oxidation state minus a number of negative charges. So a number of negative charges is being subtracted because we lost electrons. So losing electrons can then either be written like this, or we could say, well, if we just add this compound, this step on both sides, it could also be written as this: Ym1 negative. Now this is very theoretical. I don't know of anyone writing it like this, but I just want to show you as general as I can show you the difference of what it would look like. What does the reduction half reaction look like, and what does the oxidization half reaction look like? Or oxidized, what is it now? Well, oxidization half reaction looks like that. In other words, my electrons are being added to the right, or they subtracted on the left. So let's look at a few examples of this. Before I go on, if we have these two formats here, notice that N and M, if they are the same, then there is no need to balance this equation. It would already be balanced. But if N and M is not the same, I would go through a process of trying to make them the same. So for example, if the one is 2 and the other one is 3, I can just multiply everything here with a 3 to make N a 6, because it's a 2. If I multiply everything with a 3, it would be 3, 6, 3, for example, and everything here I would multiply that with a 2 to make this one a 6, so it would be 2, 6, 2, and that would give me a way of actually balancing equations. Very interesting. I think I'll look at an example, but maybe even in another video. What I want to look at here is just a few more examples of half reactions. Okay, let's look at something like copper sulfide plus nitric acid, HNO3. This will produce a salt called copper sulfate, SO4, plus nitrogen monoxide plus H2O, water. Okay, quite a big one. Let's look at each one. The oxidation states in the original. So we'll start here. Notice that sulfur has is further to the right in our periodic table, which means he has a higher electron negativity. So we'll use his charge, which is 2 negative. In order for this whole compound to be 0, copper must then be 2 positive. In this one of these 3 compounds, oxygen has the highest. It is also in the second last column, which makes it, or in third last column in the 6th column, which makes it 2 negative. There's 3 of them, which this total, so oxygen initially starts with a 2 negative charge. I think what we could do is we could just start with each one of them. So copper has a 2 positive charge, sulfur has a 2 negative charge, and then oxygen would be the next one. Oxygen has a 2 negative charge, but because there's 6 of them in here, oxygen contributes 6 negative charges initially. These are also the oxidation states, 6 negative charges. The next one would be hydrogen. Hydrogen would add electron, he would be adding electrons to the oxygens that's wanting them. So instead of, or the resultant then is, instead of having a desire for 6 electrons, hydrogen is giving 1, so we have hydrogen as a positive. Hydrogen is giving 1 electron, which means the rest of the electrons have to be supplied by nitrogen, which would be 5. Nitrogen can only supply 5. He has only 5 valence electrons, so he will supply 5, so we will have nitrogen as 5 plus. Okay, so I'm doing half reactions, so let's see which ones of them have actually undergone some changes. Afterwards, notice here, afterwards we have oxygen here. So there's a few oxygens. Some of them have undergone changes, some of them have not. Okay, the only time oxygen would have undergone change if it's oxygen on its own or oxygen with fluorine. Oxygen is not on its own here, so nothing happens to oxygen in this process. So oxygen remains 2 negative. Again, the only time oxygen would undergo reduction is if it oxidization reduction if it's on its own. Nevertheless, all of these oxygens will have 2 negative, so oxygen would have 2 negative. Here we've got 4 oxygens, so that would be 8 negative. Copper will supply 2 of them, 2 positive, and then sulfur must supply the rest. So sulfur would supply 6 positives. He does have the 6 positives because he has 6 valence electrons in his valence structure. So that's there. So let's see. Sulfur went from being 2 negative to being 6 positive. Sulfur went to being 6 positive. Here we've got oxygen is 2 negative. Nitrogen would therefore be the would have to provide the 2 electrons, so nitrogen would have a 2 positive charge. It used to be 5 positive, now it is 2, so nitrogen becomes 2 positive. Okay, in this last one, oxygen is 2 negative. Hydrogen is still providing the desire for 2 electrons with each one of it giving 1, so he would provide the 2 negative, so the 2 positives. So hydrogen remains H plus. Okay, again, it looks like it is producing 2, but it's only because there are 2 of them. Okay, with that being said, copper, we can see copper remained 2 positive, so there was no change in electrons So, or in the oxidation state for copper, we can ignore that one. There's no change for oxygen, we can ignore that one. We do, however, see that sulfur went from owning 2 extra to owing 6 electrons, which means he had lost 8 electrons. He had lost 8 electrons. Nothing changed in hydrogen. Hydrogen didn't change. Nitrogen, however, started with 5 and he ended up gaining 3, because he went from being 5 positive, owing 5 electrons, to only owing 2 electrons, which means he must have somewhere got 3 electrons. Okay, so making the positive charge less positive can only happen with 3 electrons. Now, what I wanted to show you and how we could use this is not a balanced equation, how we could use this to now balance the above equation. These are the 2 half reactions. Which one is being oxidized, which one is being reduced? Well, he's losing electrons, which obviously means he is being oxidized. See how I get confused? He's being oxidized, and then here we've got him gaining electrons, so he is being reduced. Okay, but now I would like to have this exchange be equal. In other words, I would like this 8 and this 3 to somehow correspond. What is the closest number that they can get to? That would be 24. 24. I have to multiply this with 3 to get 24, so this becomes 3 sulfurs, 24 electrons, and 3 producing 3 sulfur. Here we have, this one we'll need to multiply with 8 to get 24 electrons. Okay, so we have 8 nitrogens plus 24 electrons. I forgot the negative there, and that will produce again 8. I'm multiplying everything with an 8. Okay, so now we can see that in order to have 3 sulfurs on the left hand side, we'll have to multiply this with a 3, and then to have 3 sulfurs on the right hand side, this is where sulfur is, so we'll multiply that with a 3. In order to have 8 nitrogens, we'll have to multiply this with an 8, and in order to have 8 nitrogens on the other side, I will have to multiply this side, that's the only place with nitrogen, also with an 8. Let's see if we have the correct system going here, or in other words, the correct balancing. Sorry, lost that word for a second. Well, we see we've got 3 coppers here, we've got 3 coppers there. That's fine. The next one, we'll do oxygen last, because we can see that there's too many oxygens to take care of. So we'll do hydrogen next. We've got 8 hydrogens here. Okay, let's leave hydrogen as well, just for a second, since we didn't. If we edit this one, we're going to have to consider oxygen as well. So let's just leave it for now. Nitrogens, 8 nitrogens on this side, 8 nitrogens. Oxygen, let's see. Oxygens now let's consider hydrogen first. We've got 8 hydrogens here and only 2 hydrogens here. So we know we're going to have to edit something here to get the correct number, and we suspect it's going to have to be a 4. Now let's see what happens with oxygen. Oxygens, we've got 24 oxygens. Okay, 8 times 3. Here we've got 4 times 3 is 12 oxygens. Okay, so we need another 12. Here we've got 8 oxygens, so now we only need 4, so here we've got 1. So if we multiply this with a 4, we get the 4 oxygens that we still need, and we have the 8 hydrogens that we need. So look how this helped us to get the exact coefficients that we need for our compounds, and the ones that didn't get, we just could have edited that one to completely balance the equation. So excellent process. I'm not going to go very much further into half reactions. We've looked at what half reactions is. It's just writing the trading of electrons, or the movement of electrons, and then we looked at how to get the half reactions from an expression, and after that how to use those half reactions to actually balance an equation. Thank you very much for watching. I'll see you in the next video, and we are soon approaching electrochemistry, where this is going to be so exciting to use. See you there.